Have you ever wondered how AI actually thinks? Not just how it finishes a sentence or gives you an answer, but what's going on inside between all those neurons and predictions. You give it a prompt, it gives you a response. And it's often impressive and sometimes surprisingly thoughtful. But how did it get from A to B? That middle part, the part where the thinking happens, has mostly been a mystery. These big AI models like Claude, GPT, Gemini, they don't work the way we're used to. They're not like a spreadsheet or a search engine. And they are not following step by step instructions written by a human. Instead, they are trained. They learn by consuming massive amounts of data like books, articles, forum threads, source code, news headlines, conversations, you name it. And from all of that, they build patterns, relationships which look like strategies for figuring out what to say next. But here's the catch: even the people building these models cannot fully explain how they work on the inside. It's kind of like teaching a kid math without ever showing them how to add or subtract. The kid might still figure it out. They might develop their own tricks for getting the right answer. But you, as the teacher, would have no idea how they're doing it. That's what makes these models so powerful and so unpredictable. They learn, but they don't explain themselves. So I thought it would be great to do a mini series to dig into a new method that tries to pull back the curtain on that thinking. It's called circuit tracing, and it was introduced in a research paper released just last month in March 2025 by Anthropic, which is the team behind the Claude models. In this study, the team focused on Claude 3.5 Haiku, their lighter weight production model. And instead of just measuring performance or accuracy, they asked a different question: what's happening inside the model when it generates a response? Circuit tracing is how they went looking for the answer. It's a way of tracking which internal features activate, which ones influence others, and how those interactions shape the model's output. It's kind of like building a wiring diagram for the model's thought process. You can see how information moves, which paths light up, which parts influence which, and maybe most importantly, where things go wrong. And I want to walk you through how that works. So, our mission today is to, well, first understand this circuit tracing thing, what it is and how it works. And then we want to see what it actually tells us about how these models reason, make connections, and even improvise. Without getting bogged down in technical stuff, just clear, surprising insights. Because it comes down to something simple but profound. These models learn. They don't follow hard coded rules. They develop their own strategies based on the data they've seen. And those strategies, like that kid doing math in their own way, are not always obvious from the outside. Let me give you an example to better understand this. The researchers gave the model this prompt: the capital of the state containing Dallas is. Now, this isn't a simple question. To answer it, the model has to do two things. Step one, recognize that Dallas is in Texas, and step two, recall that the capital of Texas is Austin. This is not direct lookup. That's reasoning in steps, a small chain of logic. And with circuit tracing, they could see a specific set of internal features activate. First, ones linked to the idea of Texas, even though the word Texas is not in the prompt at all. And then another set of features connected to Austin lit up. And only after that did the model give the answer. But that's where it gets really interesting. They could actually intervene in the process. When they weakened the Texas features, the model got hesitant. Sometimes it even gave the wrong answer. When they boosted those features, it confidently answered Austin. So, what you are seeing is not just input output. You're seeing a series of internal steps, almost like mental gears turning. And that's huge because for the first time, we're not just guessing about what these models are doing. We can trace their logic. We can say this part of the model is helping it remember geography, and this part is helping it connect one idea to the other. We are finally beginning to understand the why. So, this isn't just about how models generate text. It's about how they think through problems. And that's what makes circuit tracing such a big deal. In this series, I want to share what this method is teaching us, especially from Anthropic's work on Claude 3.5 Haiku. You don't need a technical background to follow. I'm not a machine learning engineer, but I'm curious, and maybe you are too, because these systems are already shaping how we work, how we write, how we learn, and how we make decisions. And I think it's time we started understanding how they make theirs. In the next video, I'll explore how these models handle language, and not just English, but across many languages, and what that tells us about how meaning is represented inside the model. And we'll look at something deceptively simple as well, adding two numbers together, and why that's way more complicated than it sounds. See you in the next one.